Meta-Complexity.
So in this part of the morning session, I'm just going to highlight a few open problems that are sort of connected to meta-complexity, and it's on the way of sort of illustrating what I said in the previous part, where I was talking about meta-complexity as a topic and as a tool. And in terms of meta-complexity as a tool, which kind of problems in other areas is it sort of relevant to or useful for? And I'll just give you some examples. I mean, I don't expect you to kind of follow along completely. I mean, just to make you aware of some problems, and just in case you want to have something to start thinking about, something concrete to start engaging with. So problem one. So this is a problem that we've already kind of seen before. We asked in the previous talk itself, which is the NP-Hardness of MCSP, which is probably the major open problem about MCSP. So again, I mean, MCSP is a problem where you're given a truth table of a function on n variables, on little n variables. So truth tables of size 2 to little n and your parameter s. And you want to know, does F have circuits of size s? So we don't know if MCSP is NP, but at least we have some evidence about it. But we would expect that MCSP is NP hard. I mean, there aren't that many natural intermediate NP problems. I mean, there are problems like, I guess, factoring, which are believed to be NP intermediate. There's other problems like graph isomorphism, which at this point probably is believed to be in polynomial time. And this is one of the few problems left that's kind of is not known to be either NP, nor is it known to be NP hard. And there isn't really any evidence that it's not NP hard. So MCSP is one of the few problems where I think we can still hope to show NP hardness without surprising ourselves too much. And so that's the main problem here. And more generally, we can ask for which meta-complexity measures is the measure NP hard, which circuit class is C MCSP NP hard. And we defined lots of meta-complexity problems in the previous talk. So for each of them, each of those problems it's an NP, which one is NP hard? K capital T, K poly, min, KT, etc. So so what can we say about NP hardness of these problems? So for a long time, this kind of enterprise of trying to prove NP hardness, there's mostly various obstacles that were shown. So in this sort of paper of cabinets and psi, where they defined MCSP, they also showed that if MCSP is NP hard under kind of some standard kinds of reductions, deterministic honest M reductions. So deterministic reductions, mapping reductions, meaning you're kind of given X, you're kind of computing f of X. I mean, you want X to be satisfiable if only if f of X is yes instead of MCSP. And these reductions are honest, meaning they don't decrease the size too much. So the size of the reduced instance isn't much smaller than the size of the initial instance. It's at most polynomially smaller. And all the reductions we have in practice are honest. I mean, it seems unclear how you can gain from decreasing the size of your output too much. So this seems like very weak condition on the reduction to say that it's deterministic and honest. And standard NP hard problems are hard under such reductions. But if we can show that MCSP is NP hard under such reductions, then you get a kind of a breakthrough complexity result, which is that exponential time does not have polynomial size circuits. And this is something we don't know. We seem quite far from proving. So this isn't quite evidence against NP hardness. It's just sort of evidence for the difficulty of showing NP hardness. If you can show NP hardness, then you get a low bound out of it, and we don't yet know, it seems, how to get low bounds. And then there are several kind of follow-up works with similar or related results. So Murray and Williams, in fact, show an unconditional non-NP hardness result under a stronger notion of reduction. So if you look at deterministic, or I think even randomized polylog time projections, so these are quite restricted reductions where each output bit is just sort of an input bit or its complement or 0, 1. So a very restrictive kind of reduction, and where you kind of can compute which bit it is in polylog time in the input. But it seems very restrictive, but the fact is that most NP hard problems, all natural NP hard problems, seem to be hard under such reductions too. And for MCSP, we can show that it's not NP hard under such reductions. Even parity doesn't reduce to MCSP. So there's something different about MCSP. This kind of an explanation of why we found it hard to get NP hardness results. There's something different about it, and standard kind of notions of hardness don't seem to suffice. And then a recent result with Mike Sachs, we showed that, for example, even common complexity is not NP hard to approximate. If you look into approximate the hardness of approximation of common complexity to a super logarithmic additive term, you want to know whether common complexity is at least say NO2 or NO2 minus log n squared. then this is not NP-hard under randomized honest non-adaptive reductions unless the polynomial hierarchy collapses, which would be very surprising. So, so even if you have randomized reductions, there are some sort of like, sort of surprising consequences of showing hardness under such reductions. So yeah, there's just two. I mean, there's many other results. So there's like a whole body of work on this, and yeah, in the past 10 years, there's lots of results of that nature. However, none of these results, for me, really count as very strong evidence against hardness. They're kind of like evidence for the difficulty of showing NP-hardness, but not really evidence against. I mean, of course, these results are evidence against hardness with certain kinds of reductions, but why restrict ourselves to reductions of this kind? We can kind of consider adaptive reductions or non-uniform reductions. There's absolutely no evidence against randomized adaptive reductions or against non-uniform reductions. And in fact, like a couple of the results that I mentioned to you in the previous talk, the results about k little t and k capital S, these problems are hard for exponential time and polynomial space respectively, and they're hard under non-uniform reductions or under adaptive reductions. So like the cases where we know how to show hardness, those are under stronger kinds of reductions. So why not use those kinds of reductions to try to show that MCSP is NP-hard? Well, not that people haven't tried, but they haven't been successful so far. But especially over the past 3 or 4 years, there's been a lot of progress towards this. So, I mean, so a very old result of Masek is that DNF MCSP is NP-hard. So for C, MCSP with C is DNFs. Then over the past 2 or 3 years, there have been like many other results. So variants of MCSP or meta-complex problems, which haven't really defined, but are fairly intuitive. So Rahul Ilango showed that the minimum oracle circuit size problem, where you're given a truth table together with an oracle, and you want to know whether the truth table has small circuits relative to this oracle, that problem is NP-hard. So if you have this additional oracle as well, rather than just a truth table, then that problem is NP-hard. So Ilango, Loff, and Oliveira show that multi-valued MCSP is NP-hard. So here you don't have Boolean circuits, but circuits with a large output. And you want to know whether there's a small, so instead of a truth table, you have a table of values, each of which is an output of the circuit. And you want to know, is there a small circuit consistent with this table? So it's sort of generalization of MCSP from Boolean circuits to multi-valued circuits. And that's NP-hard as well. All of this under randomized reductions. Then Ilango showed that AC0 formula MCSP is NP-hard. So a significant sort of like an extension of this result of Masek. So this is for formulas of depth 2. And now we know for formulas of any depth that formula MCSP is NP-hard. And yeah, and another result that Rahul showed is that minimum formula size problem. So if you have formula MCSP, you want to know whether a truth table has a small formula or not. That's not known to be NP-hard, but it's hard in the exponential time hypothesis. So if K-stat requires exponential time, then this problem is hard. And Rahul is going to be talking in more detail about these results and the techniques involved in them tomorrow. So there's several new techniques, interesting ideas that come into this. Liu and Pass showed that there's a conditional version of K-poly. So I kind of talked about conditional versions of polynomial complexity briefly in the last talk, where now instead of asking the complexity of a single string, you ask for the complexity of a string relative to some other string. Is there a short program for computing X from Y, given some Y, that runs in polynomial time? And this version is NP-hard as well. And then most recently, Hirahara last year showed, I think the result that comes closest to actually settling the NP-hardness, which is that partial MCSP is NP-hard. And if you think about it, this problem seems very close to MCSP. MCSP is a truth table with zeros and ones. Here you have zeros, ones, and don't knows. And with don't knows, you kind of like, the circuit can output either 0 or 1. So that seems very close to MCSP, and we know that that's NP-hard.
Under which reduction?
Randomized reductions. So under randomized, many one reductions. And one difference between this result and the others is that the other results do give some hardness approximation, but very small approximation factors. Say less than kind of like log n multiplicatively in general. While Hirahara's result sort of like seems to be able to, this technique seems to be able to work with larger approximation factors. So that's on the sort of interesting feature of his result. And at this point, given all this recent progress, there's pretty much nothing else left to do but show that MCSP is NP-hard. So not to put too much pressure, but yeah. The problem too, so just kind of like moving away from complexity theory and going into learning theory. So here's the problem about learning circuits. So we still don't fully understand which circuit classes are learnable and which ones are not. So in particular, if you consider the class of circuits with so unbounded Fano and mod n gates, say mod 6 gates, some composite modulus, is there like an efficient algorithm for learning such circuits from random examples? So let's say you're given kind of examples from the uniform distribution, and you want to learn a hypothesis that predicts these examples well, or the uniform distribution that has good agreement with or the uniform distribution. And you're allowed to ask membership queries. So you're allowed to ask for your hypothesis what its value is on any x, and then you have to output sort of like a hypothesis that agrees with the true circuit. So is that an efficient algorithm, quasi-polynomial time algorithm, to do this? So yeah, this is one example of an open problem in learning theory. And so this is kind of like more of a looking for a positive result. So far we've been talking about hardness and low bounds. So here is a potential application of meta-complexity and getting positive results. And the model for this is this paper of Carmosino, Impagliazzo, Cabinets, and Kolokolova, where they showed like this really kind of like interesting result for A0 mod P circuits. So for a long time, it's been known that AC0 circuits are learnable in quasi-polynomial time, but it wasn't known how to extend this to A0 mod P circuits. And CIKK showed this for any prime P. And still open though for larger circuit classes, and even for some circuit classes that are incompatible with A0 mod P. So you might ask, well, what does this have to do with meta-complexity? I already briefly said to you, mentioned a reason why meta-complexity might be relevant, but here, let me kind of expand on it a bit. So CIKK derived their learning algorithm by establishing connection from natural proofs, which are very much a meta-complexity notion, useful against a circuit class, and learning algorithms for the circuit class. So if you have like a proof low bound technique against a circuit class, and that yields a natural proof against a circuit class, you can then transform that to a learning algorithm for the circuit class. So there's like a close relationship between complexity low bound techniques yielding natural proofs and learning algorithms. And as I said in the previous talk, natural proofs useful against C is essentially a zero-error average case algorithm for C MCSP, or the uniform distribution. So it's very closely tied to meta-complexity. So by their kind of like result, for any large enough circuit class C, natural proofs useful against sub-exponential size C circuits imply quasi-polynomial time learning algorithms for C. And now if we kind of like consider C equals ACC 0, we do know how to show lower bounds here, but the problem is we don't know how to get lateral proofs against circuits of this size. And kind of like Williams results in the algorithmic method, we know how to get like low bounds on x to the NP against sub-exponential size ACC 0 circuits, but we don't yet know how to get natural proofs. So we don't know how to analyze these low bound techniques in a way that we can get natural proofs from them. And if we did, then we'd be able to get our learning algorithm for these classes. So that's about getting learning from low bounds. And we could also think of like reversing the connection, about getting new low bounds from learning. This kind of connection that I told you about allows us to derive learning algorithms from low bound techniques that yield natural proofs. And in fact, you can even reverse the connection. So there's a line of work, and a paper of mine with Igor Oliveira is one of the more recent ones, where you can get low bounds in BPX from non-trivial learning algorithms. So any learning algorithm that runs in less than brute force search can be used to get a low bound in BPX against a circuit class. So for example, if you could derive non-trivial learning algorithms for these circuit classes, ACC 0 or DEPS2 TC0, these are sort of frontier classes in terms of proving low bounds. These are the classes where we don't have any sort of explicit low bounds. Then we would get some new information, for example, that BPX was not in C. And in fact, this connection from learning to low bounds holds even for quantum algorithms. So in kind of a recent work, it was shown that even quantum algorithms that are non-trivial learners give you low bounds in quantum version of exponential time against C. So it seems like a fairly kind of robust connection. Yeah, so with each of these questions that I mentioned, there are other questions related to them that are kind of interesting to attack as well. So here, the main question is about getting a new learning algorithm, but you could kind of reverse that and try to get like a new low bound as well. That's question 2. So problem 3 is sort of like trying to use meta-complexity as a hardness assumption. So like we've used many different hardness hypotheses in complexity theory. And of course, the most popular is NP not equal to P and NP hardness. There's also the unique games conjecture to try to understand inapproximatity of various approximation problems. There's Feige's hypothesis, which is kind of an average case hardness assumption. There's the existence of one-way functions, cryptographic hardness assumptions. And then there's sort of fine-grained hardness assumptions, such as the exponential time hypothesis and the strong exponential time hypothesis. The exponential time hypothesis says that KSAT requires like time 2 to the omega n, and the strong expression time hypothesis kind of says that it requires time like close to 2 to the n as k increases. So these assumptions are used in various contexts in complexity theory to classify the hardness of problems where we don't quite know NP hardness, or to get strong approximation factors. So for example, hardness approximation, learning, fine-grained analysis, and so on. So there's a host of hardness assumptions that are used. And something that hasn't been done very much is to use hardness hypothesis based on meta-complexity assumptions, right? So these are, so for example, the impossibility of circuit size in polynomial time up to a large factor, or maybe even in sub-exponential time up to a large factor. Perhaps this can be used to get to unify some of the results that have been shown already with the hardness hypothesis listed here. Let me kind of zoom in on one of those, Feige's hypothesis. So Feige hypothesized that K-SAT is hard to solve in an average case sense. So let's say you're given a CNF that's generated randomly. Each of the K clauses is generated completely uniformly at random. There's a linear number of them, and each of them is generated completely uniformly at random from a set of all K clauses. And the question now is, well, you want to certify that this formula is satisfiable or unsatisfiable, and you want to correctly certify a non-negligible fraction of these instances, and you don't want any instances to be wrongly certified. So that's what it means to solve this problem on average. And if you assume that this is hard to do, I mean, yeah, we don't really have worst case to average case hardness for K-SAT, so we don't know that this follows from NP hardness, but let's assume that this problem is hard. Then you can get some stronger interproximity results for various problems, such as like densest case subgraph, maximum bipolar clique, and so on. And we have no good hardness results in terms of NP hardness for these problems. So, so there's this paper of Feige, there's a follow-up paper of Aleknovich. So there's some work on these kind of like average case hardness assumptions, which give you stronger interproximity and results. And then there's also results for hardness of learning based on similar hypotheses. So Danelli and Shalev-Schwartz, and there's been some follow-up work recently. They showed learning of hardness of packed learning DNFs based on similar hypotheses, except that now it's not a linear number of clauses, but some superlinear number of them that you have hardness for. So Feige's hypothesis is related both to hardness of approximity and to learning, but it's an average case hypothesis. So one question is, maybe you could replace Feige's hypothesis by a meta-complexity hypothesis. So I showed with Shuchi Hirahara that Feige's hypothesis implies hardness of MK capital TP on average. So if you use this as a hardness hypothesis, that would give you a stronger result. But perhaps you could even use like inner proximity for MKTP, a worst case hardness assumption rather than an average case hardness assumption. And intuitively, these reductions of Feige and Danelli and Shalev-Schwartz in the previous slide, they do exploit compressibility. I mean, the way they use their average case hardness assumption is using compressibility. So perhaps some kind of meta-complexity assumption would be useful as kind of replacement, might be the right thing to use in order to get results of this form. So I think this is a direction that's not been explored very much and might be a productive one to look at. Okay, so yeah, so the next two kind of like directions relate to kind of average case complexity. And before kind of like talking about them more, I'd just like to remind you in case you've seen it before, or to tell you about the 5 worlds of average case complexity defined by Impagliazzo in a survey in 95, a personal view of average case complexity. So it's a very influential survey. So essentially, like this survey talks about these different kind of like worlds based on our kind of like ignorance about the truth of complexity theoretic statements. So algorithmica is a world where NP equals P, so where NP is easy. So, I mean, of course, there's lots of advantages to that world, but we can't do kind of like crypto in that world. We could do obfuscation, but no other crypto. So algorithmica is a world where NP equals P. And then there's heuristica, where NP is worst case hard, but NP is easy on average, right? So this line here, so as you go along this line, the complexity assumptions get stronger and stronger, from worst case hardness of NP to average case hardness of NP to one-way functions existing to public key crypto existing. And really, it's the question of whether you're in between two of these assumptions. So here, you have worst case hardness of NP because you're to the right of this point, but you have average case easiness of NP. So heuristica is a world where NP is average case easy and NP is worst case hard. And we don't know how to rule that out. We don't know any worst case to average case reductions for NP. So we don't know how to rule out the existence of heuristica. And then there's this question of like, okay, suppose you did have average case hardness, can you get any crypto from it, right? So there's this world Pessiland, which is some of the worst of all possible worlds, because if you, in Heuristica, you have average case easiness, so you can solve problems on average, and that seems like a good thing generally. Here, you can't solve problems on average in NP on average, because NP is average case hard. But you also don't have crypto. So you neither have crypto, nor do you have average case solvability of NP. So that's kind of like a very pessimistic world, Pessiland. Then there's minicrypt, where you know that one-way functions exist, but you don't have stronger kind of crypto system. You don't have public key crypto. And finally, cryptomania, where public key crypto exists. And of course, you could kind of come up with many other worlds, depending on which complexity kind of statements, assumptions you're interested in. So, I mean, the current state of complexity theory is sort of like two, we certainly can't hope to solve P versus NP. So we don't know whether we live in algorithmic or not. So there's no hope of kind of like figuring out precisely which world we live in. But we could hope to kind of eliminate or get rid of some of these intermediate worlds. And doing that would correspond to coming up with new reductions, right? Like showing that this follows from this, or showing that one-way functions existing follows from NP being hard and average, or the public key crypto existing follows from one-way functions existing. So that would be a way to kind of like annihilate these worlds in between, to get rid of minicrypt or Pessiland or Heuristica. And these are, I mean, of course, the important questions in average case complexity and crypto. And it turns out that meta-complexity is kind of like a useful kind of like tool to kind of address some of these questions. So here's problem 4. So problem 4 is kind of like ruling out Heuristica. So we have here Heuristica, which is that NP is hard in the worst case and is easy in the average case, and we want to rule that out. So we want to show that worst case hardness of NP implies average case hardness of NP. Does worst case hardness of NP imply average case hardness of NP? So this kind of like question of worst case to average case reductions is one that's been studied a lot in complexity theory, and we know quite a lot about this question. We know that, for example, like problems in polynomial space and exponential time have worst case to average case reductions. They have random self reductions, which give you worst case to average case reductions. We also know it for some problems that are kind of like quite weak complexity wise. So for example, if you look at like problems in logarithmic space or NC1, and you look at them with respect to weaker circuit classes, then those problems have worst case to average case reductions too. But in between, we don't really know. So for polynomial time, for NP, for polynomial hierarchy, we don't really have a sense of whether there are worst case to average case reductions. When you kind of like define this question, you could define it in many possible ways, because your worst case hardness could be with respect to any of these classes, to deterministic polynomial time, to zero error probabilistic time, bounded error probabilistic time, or even just non-uniform polynomial size. And the average case hardness could either be a zero error version, where the algorithm is required to be correct and never make a mistake, or bounded error, where it makes mistakes with some small probability of the distribution. So yeah, there's many possible versions you could define. And it would be interesting to get an implication for any of these versions. We don't really have like an implication for worst case hardness to average case hardness for any of these versions of the problem. And there's kind of reasons for this. So there's like various kind of obstacles to doing this. So I mean, these obstacles kind of indicate that the techniques we know for like larger classes, such as polynomial space and exponential time, can't be used for NP. So Bogdanov and Trevisan, building on Fortnoy and Feigenbaum, showed that there's this notion of a black box non-adaptive worst case to average case reduction, which like the known reductions for polynomial space and exponential time do satisfy. And such reductions don't exist for NP unless the polynomial hierarchy collapses. So what is a black box non-adaptive worst case to average case reduction? Well, like if you want a worst case to average case reduction, you're starting off from some NP problem, NP hard problem, say SAT, and you want to construct some problem L and a distribution mu such that that problem L is an NP and is hard over mu on average, right? And the black box means that given any algorithm for L over mu, the algorithm that you then get for SAT uses this algorithm in a black box way. So given any sort of algorithm A for that solves L on average, you're able to use that in a black box way to solve SAT in the worst case. That's what black box means. And non-adaptive just means that that you don't make adaptive queries to the algorithm. So so this is kind of like a natural notion, and it turns out that this notion is impossible to achieve for NP unless the polynomial hierarchy collapses. So that's one kind of obstacle. There's also other kinds. So there's a relativization obstacle. So Impagliazzo and Watson show that worst case to average case reductions for NP can't relativize. There's oracles relative to which they fail. There's oracles relative to which NP is very hard on average, but very easy. Sorry, very hard in the worst case, but very easy on average. There's also other kinds of evidence. Viola gave evidence against hardness amplification within the polynomial hierarchy. So if you want to go from like a problem L to a problem L prime, and L prime is sort of like is in the polynomial hierarchy with orcal access to L. So if you want to go from worst case hardness for L to average case hardness for L prime, and L prime is the polynomial hierarchy with orcal access to L, then that actually implies average case hardness unconditionally. So that's Viola's result. So there's kind of like various kind of like pieces of evidence that this might be hard to achieve. And meta-complexity has been used to make kind of progress on this in various ways. So so there was sort of like building on this kind of like on the influential work of Kamoisino, Parzo, Kavnes, and Kolokolova, there was some worst case to errorless average case reductions for meta-complexity problems. So yeah, we don't have any sort of like leads on getting worst case to bounded error average case reduction. We don't know anything about that question at all. But for errorless average case hardness, we do have some reductions for these meta-complexity problems. And these are meta-complexity problems which are not believed to be in co-NP. So if we could show that these kind of problems were NP hard, then we'd be done, because that NP hardness would imply average case hardness, right? There's just one detail, which is that like we don't quite get a worst case to average case reduction, but we get a reduction from approximating these problems to average case easiness. So if these problems are hard to approximate, we get average case hardness from that. And so we need to show a stronger NP hardness result for approximability in order to rule out heuristica using these results. So that's one direction, but it already gives you some new information that there are these problems which, which look hard and which do have worst case to average case reductions. Then there's sort of like this result of Hirahara where he showed that if there's like a worst case assumption, which is kind of like a very strong worst case assumption. So UP, so the class of problems that are in unique polynomial time, or there's a unique witness for the S instances, if that's not in time 2 to the order n over log n, that implies an NP not in P on average. So it's kind of like a strong worst case hardness assumption, but then you get an average case hardness conclusion from it. And kind of what's interesting here is that the statement of this result doesn't really refer to meta-complexity at all, but the proof techniques do rely heavily on meta-complexity. So it seems that meta-complexity is somehow kind of an important notion here to understand the status of this question. And there's sort of like a randomized kind of like version of this result too, more recently. Like if you have like a randomized worst case assumption for UP, you get like a randomized average case conclusion for NP. So yeah, so there's some progress, and in order to completely rule out heuristica, we need to prove some kind of like NP hardness results, which we don't know how to show. We don't even know how to show NP hardness of MCSP without any approximation factor. So that's a first step, but perhaps eventually there might be a way of showing strong enough NP hardness result that you can combine it with these reductions to get that heuristica doesn't exist. Questions for me? So that's yeah, so that's about heuristica. And then yeah, there's also this question about Pessiland. So like, does the average case hardness of NP imply that one-way functions exist, right? So yeah, it's kind of fairly standard that one-way functions imply the average case hardness of NP. So if one-way functions exist, then NP is average case hard. And the question is whether you can kind of like yeah, get a converse. Can you get one-way functions existing from arbitrary average case hardness of NP? We do know for very specific problems that the average case hardness of these problems implies existence of one-way functions, like factoring, for example, or discrete log. But yeah, but these are for specific problems, and we're interested in just the general assumption about average case hardness of NP and whether that's sufficient for one-way functions existing. And there's some kind of like evidence also that this might be hard to do. There's like relativized worlds in which this doesn't exist, meaning that there's relativized worlds where NP is average case hard, but one-way functions don't exist. So any proof technique that's used here can't relativize. So that's sort of like a bottleneck in attacking this question. And again, there's sort of like some progress via meta-complexity. So the kind of the most significant work here is by Liu and Pass, who kind of like characterized one-way functions by an average case hardness assumption on polynomial time-bounded Kolmogorov complexity. So they show that one-way functions exist if and only if polynomial time-bounded Kolmogorov complexity is hard in a certain sense on average over the uniform distribution, in a certain bounded error sense over the uniform distribution. So this is kind of like, yeah, kind of a breakthrough because it sort of allowed us to characterize one-way functions completely using meta-complexity. And then there's been other characterizations since. One-way functions exist if even Kolmogorov complexity, which is an uncomputable problem, is hard on average over any sample distribution to approximate, or if the minimum circuit size, if circuit size is hard on average to approximate over so-called locally samplable distributions. There's many characterizations of this kind. And these characterizations kind of like open the way towards possibly ruling out Out Pessiland, because if you could show that as kind of a reasonable distributional version of this problem is NP-hard, then or hard for average NP, then you'd be done. And Liu and Pass have kind of like a result towards that, where they have this problem, the conditional version of K-poly. They show the problem is NP-hard, and they show that if this problem is hard on average with a uniform distribution, that implies that one-way functions exist. So on first sight, looking at this result, you might think we are done. I mean, here's an NP-hard problem, and its hardness on average implies that one-way functions exist. But the problem is that by hardness on average of NP, you mean over some sampleable distribution, not over this specific distribution that they pick here. So in order to rule out Pessiland, you need this to hold for, you need this implication to hold even when you have any sampleable distribution here, not just hardness over the uniform distribution. So that's the gap between what's known so far and what we need in order to rule out Pessiland. But again, it seems we made some progress there using ideas from meta-complexity. Note again that this question on the surface doesn't seem to have anything to do with meta-complexity, but the techniques used are yeah, closely related to meta-complexity. Any questions about Pessiland or Heuristica? Okay, so yeah, a couple more problems about that are more crypto related. Yeah.
Go back. You said this doesn't look like related to meta-complexity by the statement, but MCSP and K-poly is by definition meta-complexity.
Oh, sorry. I mean, the question of ruling out Pessiland doesn't seem obviously related to meta-complexity. Yeah. So yeah, the question of ruling out Pessiland is an obviously meta-complexity question, but the techniques used are meta-complexity techniques. Yeah. Yeah, because yeah, the sort of like the broad theme of this talk is how meta-complexity plays a role in areas where it might not obviously seem to be. Yeah, and then so there's this kind of like, so this isn't that precise a question perhaps, but I think it's an interesting direction to look at. So are there like are there a variety of natural distributional problems? So average case hardness characterizes it's characterized by the existence of one-way functions, characterizes the existence of one-way functions. So where there's an equivalence between average case hardness and existence of one-way functions. And the motivation for this question is sort of like in analogy to NP completeness, right? So part of the reason why SAT is such an important problem is because it's NP complete and because it can be used in so many interesting reductions, right? So Cook and Levin showed that SAT is NP hard, but if they'd only showed that and then there wasn't progress after that, well, SAT wouldn't be such an important problem. What really kind of like pushed the field further was results of Karp and others showing that all these other natural problems, combinatorial problems, and problems from other domains are NP hard. So SAT kind of like gives you a problem to reduce from to and show that many other natural problems are NP hard. So in terms of worst case complexity, we have like a very clean picture of what's NP complete and what's not. Of course, we don't know it yet for the MCSP related problems. For most problems, we know whether they're NP or they're NP hard or they're unlikely to be NP hard. But this is far from being the case with average case complexity. So you have like a variety of problems and distributions, and it's quite wild in the sense that it's not really clear like whether natural problems with natural distributions on them are hard or not. So that's kind of like quite unclear. So I think this result of Liu and Pass showing that Kolmogorov complexity, the polynomial time-bound Kolmogorov complexity or the uniform distribution, that's in a sense one-way function complete, right? It's kind of hard if and only if one-way functions exist. So let me just refer that as one-way function completeness for now. So that was given by, that result was given by Liu and Pass. And then there's further problems given in follow-up work. But all of these problems are meta-complexity problems, right? So they're all sort of connected to Kolmogorov complexity and variance of it and kind of like approximating it over natural distributions. It's, yeah, that's nice, but is there a natural distribution problem that's not of a meta-complexity flavor and is equivalent to these, right? So that's not so clear. And that's what we'll be looking for. I mean, there's lots of natural, interesting average case complexity problems, distributional problems, and can we show for some problem that's defined combinatorially or in some other way that is equivalent to one-way functions existing. So that would be like the analog of Karp's theorem in the setting of average case complexity. So yeah, so that's the question here. Is there a natural distribution problem with normal meta-complexity theorems equivalent to these? And part of the motivation is simply that we don't really have many techniques to get average case reductions. We don't have many techniques to reduce distributional problems to each other. So Levin has this kind of theory of average case complexity where there are notions of completeness and there are complete problems, but they aren't, there aren't many natural complete problems. And in many cases, we don't know if reductions exist. So for example, we don't even know if the reduction between 3-side and 4-side of the uniform distribution. Even these questions seem kind of like the answer seems unclear. So given this sort of like lack of information, I mean, maybe one path towards achieving such reductions, average case reductions, is by characterizing these hard distributional problems using crypto primitives or using other primitives. So if you can show that the one, say, this hard distributional problem A is equivalent to the existence of one-way functions, and some other problem B is also equivalent to the existence of one-way functions, then you know that A and B are reduced to each other, though that might not be easy to see otherwise. And in fact, yeah, this path was taken to show the equivalence of various distributional meta-complexity problems, which superficially look quite different. Now we know that they're all equivalent with regard to their complexity because they're all equivalent to the existence of one-way functions. But can this sort of like technique be applied to other natural problems, like combinatorial ones, like maybe versions of planted clique or versions of like Feige's hypothesis problems like that? It'd be interesting to get any example of that kind. Yeah, so I'm covering quite a kind of like a wide, I mean, a lot of territory here, but I mean, the point is not to kind of like completely understand everything, but to kind of pose questions that sort of one or two of these might interest you and allow you to get a handle on kind of like connections with meta-complexity. So that's really the goal. So if something's unclear, that's perfectly fine. And many of these things, I should remark, will be kind of like addressed and followed up in further talks. So for example, what I said about learning will kind of like be addressed by Valentin later today. And what I said about heuristica, Shuichi's talk will address that. I mean, the first problem on NP-Hardness, Rahul Longo's talk will address it. And these problems that I just mentioned, related things will be addressed by Tal and Raphael. So there will be more on these topics later in the bootcamp. So yeah, this problem 7 is a question of basing other cryptographic primitives in meta-complexity. So far, most of the work on crypto as meta-complexity has been about one-way functions, about kind of characterizing one-way functions. And the problem is, are there natural assumptions that yield other cryptographic primitives like trapdoor functions or collision-resistant hash functions, or maybe even indiscriminate obfuscation? So are there kind of meta-complexity notions that are connected to these crypto primitives? So we've been successful in characterizing OWFs in multiple ways, but there's been limited progress on other primitives so far. And yeah, I mean, I'm not an expert at all on obfuscation, but just to say a little bit about it. So an indiscriminate obfuscator is just an algorithm which applied to any two programs that are functionally equivalent. It produces programs that are completely indistinguishable. So so it's kind of like it obfuscates these programs so that you can't really tell anything about them apart from their input-output behavior. And intuitively, this is about the difference between white box and black box computation. So like a program, I mean, it's sort of like a white box object, but then you kind of process it in a way so it becomes a black box object. You can't tell anything about what the program initially was like, only about what it can compute. So it seems as though meta-complexity ideas should be somewhat related to this, but we just don't have many results along these lines yet. So yeah, and only recently have we kind of achieved indiscriminate obfuscation with standard assumptions, though there's been kind of a lot of work on that even more recently. And it would be interesting if there were kind of like meta-complexity assumptions that came into the picture to simplify these characterizations or played a role here. One result we do know is that indiscriminate obfuscation is related to the connection between MCSP and SAT. If IO exists, then if MCSP is easy, then NP equals P. And that's in like an old paper of Komorgotsky and all, and in a paper of Impagliazzo, Cabinets, and Volkovich. So we do, I mean, there's some work on it, but not very much. And I think there's an opportunity to explore these connections further. So the last three problems are going to be about like proof complexity, logic, algebraic complexity. So yeah, kind of like shifting areas again. Yeah, so here the emphasis is on kind of like the question of proving proof complexity low bounds. So we've seen already in the previous talk and that circuit complexity low bounds are closely tied to understanding meta-complexity further through natural proofs and through other connections. But what about proof complexity? So the problem here is to give complexity theoretic evidence against the efficient provability of low bounds for proof systems such as Frege or extended Frege. So we've tried very hard, just as in circuit complexity, to prove proof complexity low bounds, and we've kind of like failed even more badly in a sense. I mean, it's turned out to be even harder to show superpolynomial low bounds for propositional proof systems than for corresponding circuit classes. So for example, we have low bounds against AC0 mod P circuits, but we don't know any low bounds for propositional formulas in the proof system A0 mod P Frege, where it's the version of the Frege proof system where the lines are A0 mod P circuits. So this is still unknown. So we seem to be kind of like behind the state of the art in circuit complexity. At least in circuit complexity, there are barriers of various kinds. There's a relativization barrier, natural proofs barrier, the algebraization barrier. In the proof complexity world, there isn't even satisfactory kind of barriers. So they're not very many. There aren't any good explanations of this. There have been some conjectures that sort of low bounds are hard to show efficiently in Frege, extended Frege due to Krajicek and Rasbrov, but these are just conjectures. And the point is to tie these conjectures to other complexity theoretic questions somehow. So, and you might ask, well, how is meta-complexity sort of involved here? Well, so far, as we've discussed, meta-complexity is about the computational complexity of problems that are themselves about computational complexity, but similar ideas and techniques will be useful to study the proof complexity of formulas that are about proof complexity. So formulas that express proof complexity low bounds or kind of related to proof complexity. Yeah, this is in a sense a very, very similar task. And that's what's sort of involved here. And there's some kind of recent progress where for some like very strong proof systems, some proof systems that are even kind of non-explicit, you can show that low bounds for these proof systems are hard to show propositionally in any proof system. And you can also show some sort of limitations of showing that NP is not co-NP / poly on average in sort of bounded arithmetic. So there's some work on kind of like the hardness of proving like proof complexity low bounds, low versions of NP versus co-NP. But none of these results so far address Frege or extended Frege. Therefore, other proof systems, when there's a result for the ideal proof system, which is maybe the most concrete of these proof systems so far, but it would be nice to get some kind of information about how hard it is to show Frege or extended Frege low bounds. So from the point of view of meta-mathematics and proof complexity, this would be a natural direction to approach. Okay. Problem 9. So yeah, so this is another kind of problem in proof complexity, which is sort of at the other end of the spectrum. So Frege and extended Frege are strong proof systems where we can prove many of the things we do in complexity theory. And then there's resolution, which is a much weaker proof system. But it's of course a proof system with a lot of practical sort of impact because, like, for example, clause learning, which is one of the most popular ways of doing SAT solving, can be formalized within it. So it's very kind of like important to understand how hard it is to produce or compute resolution proofs when short ones exist. And that's what this notion of automatability is about. It's about proof search. So if you know that a short proof exists for a propositional formula in a propositional proof system, how hard is it to find, right? Yeah. I mean, this sort of like might remind you of like what I said about learning in the previous talk, where learning was really about solving the search version of MCSP. I mean, like if there's a small circuit, can you find it efficiently? And this is kind of like an analog of that in proof complexity. If there exists a short proof, can you find it efficiently? The standard notion of automatability asks you to find a short proof in time polynomial in the size of the proof. And that's the standard notion that's studied, but there's kind of like a weaker notion where if there's a system, I mean, like there's some system R that you want to find proofs in, but you don't necessarily want to find an R proof. You want to find a proof in some other proof system, like some other proof system Q, which might be stronger. And as long as it's a proof in some system and you can check it, maybe you'll be happy. So you don't necessarily want to find a proof in R. It's just as long as a small R proof exists, you want to find a proof in some system Q. So that's a weaker notion. And so it requires stronger assumptions to rule out. And it would be extremely interesting if resolution were weakly automatable. So that would be kind of like an amazing result, but we don't really know the status of that yet. And the question is to give complexity theoretic evidence for or against the weak automatability of resolution. And I mean, recently, like just a couple of years ago, it's been shown that automaticity of resolution is NP-hard, and that's an amazing result. It was an open problem for a very long time, and it was kind of solved in spectacular fashion by Atzerias and Muller. So there's been a sequence of works over the years giving evidence against weak automatability, but there's mostly cryptographic evidence for systems that are strong, like extended Frege, even constant depth Frege. And then there's even like connections with game theory. But this recent work of Atzerias and Muller shows that if you're looking at kind of the standard notion of automatability is in fact NP-hard. And in fact, what's shown is that it's kind of like NP-hard to approximate the proof size and resolution to even the very large factors, essentially the best possible result. So this is about automatability, and the question now is, what can you say about weak automatability for resolution? We really don't know much about weak automatability for resolution. And what about the role of meta-complexity here? Well, I mean, proof search is sort of like intuitively tied to meta-complexity. It's about the computational complexity of finding short proofs. But additionally, the proof technique of Atzerias and Muller uses sort of meta-complexity ideas, and that's the case with follow-up work on this as well. So we'll hopefully hear about this more in Susanna's talk on Friday, maybe a bit in Tony's talk as well. I think this is like a particular target problem, but there are kind of like other problems here about automatability which are still unsolved. And then finally, a problem about kind of algebraic natural proofs. So like we've looked at like the standard notion of natural proofs due to Rasbrown and Rudich. I haven't said very much about them, just about how they're connected to meta-complexity. I just want to say that like meta-complexity is relevant also to questions in the algebraic world. Like Ido asked about the algebraic world at the end of the previous talk. So for algebraic low bounds, I mean, are there like meta-complexity ideas that are kind of relevant there? And a concrete problem here is to give complexity theoretic evidence that there are no algebraic natural proofs against polynomial size algebraic circuits, right? So in the Boolean setting, Rasbrown and Rudich showed that one-way functions exist. Then there are no natural proofs useful against polynomial sized Boolean circuits, I mean, superpolynomial sized Boolean circuits. And that's been a very influential result in Boolean circuit complexity. It's sort of like stopped people from trying for circuit low bounds for a while. And so it kind of really kind of like tells us about the meta-mathematical aspects of circuit complexity. And we don't really know very much about this in the algebraic setting. Is there an analog of this result in the algebraic setting? And so let me say a little bit more about what I mean here.
Over which field?
Sorry. Yeah, let's just say that you're working with some field characteristic zero rationals. Natural proofs like Boolean versus algebraic, just to say a bit more about what I mean. So what is the natural proof in a Boolean setting? It's just sort of like an efficiently computable property of truth table. So you have like some property of truth tables of Boolean function. And this property is only satisfied by hard truth tables, those that don't have small circuits. And moreover, a kind of a non-negligible fraction of such truth tables satisfy the property. So 1 over polynomial in capital N, where N is the size of the truth table, fraction of truth tables satisfy this property. That's what a natural proof is. And it turns out that for like the standard combinatorial algebraic techniques for proving low bounds against weak circuit classes, you can extract from them a natural proof against a circuit class. But you can't hope to do that with general Boolean circuit low bounds if you believe in cryptography. So there's been a kind of an algebraic version of it that's sort of like studied in these two papers, where, I mean, just as a natural proof, it's sort of a property of truth table, they consider these meta polynomials, which are polynomials whose variables represent the coefficient vectors of other polynomials. And you want these polynomials to be non-zero only on the coefficient vectors of hard polynomials. So you want them to vanish on all the easy polynomials and to be non-zero on the hard ones. Just as natural proofs are properties that are satisfied by hard truth tables and not satisfied by easy ones. Here, the polynomials are zero on coefficient vectors of the easy polynomials. So it's like a natural analog in the algebraic world. And it turns out that known algebraic low bound techniques also yield natural proofs in the algebraic setting. So that part of it is interesting. But it's unclear how to formalize and argue about like crypto in this setting. So about getting like negative results. So is it the case that algebraic low bounds in general are hard to prove or not? It's unclear. Yeah.
Is there an analog of like largeness, non-negligible fraction that holds for the known?
It holds automatically in the algebraic version because of short zipple. So like
largeness.
Basically, density comes for free in the algebraic setting. So yeah, so it's kind of unclear how to formalize an argument with crypto. Is there a notion of crypto in the algebraic setting? I mean, these are questions that have been kind of looked at by various people, but there's no kind of satisfactory answer to it. So essentially, we have no evidence that algebraic natural proofs don't exist. It could be that algebraic natural proofs just exist. That's a possibility too, but that seems too good to be true. So there's been some kind of like recent kind of work kind of like addressing these questions. So and this it's kind of conflicting evidence. So there's like this paper which gives kind of like algebraic natural proofs that are useful against circuits with bounded coefficients, but it's unclear how much it says about general algebraic circuits. I mean, that's, yeah, so it's unclear whether that gives any evidence that algebraic natural proofs in general exist. And then there's this other paper by a subset of the authors, which shows that under a standard hardness assumption, the permanent is hard, then there are no algebraic natural proofs useful against VNP. So VNP is just the class of polynomials that are reducible to the permanent. I mean, of course, we want to prove low bounds against VP, I mean, against polynomial size algebraic circuits, not against the permanent. So this isn't really telling us all that much, but these are sort of like conflicting pieces of evidence. It's unclear where the truth lies. They don't give clear evidence either for or against the existence of algebraic natural proofs. And what I think this tells us is that, yeah, maybe algebraic meta-complexity needs further study to understand like the meta-mathematics of algebraic circuit low bounds better. So yeah, so that's just kind of a cross selection of problems, I mean, which kind of ranges quite widely across areas. I mean, there's many others that, yeah, didn't get time to cover. I mean, problems about like, is there a proof of the PCP theorem using meta-complexity, or problems about quantum convolvable complexity and so forth. So there's many others, but just to give you a sense of like how broad the field is potentially, and also hopefully to kind of interest you in one or more of these problems, so that you can get a handle on what this semester is about. And as I said before, I mean, most of these directions, these problems will be followed up in other talks in the boot camp, and yeah, you'll hear about them again.
Questions?
Oh, I think for the network proof data result by way of saying activity is not avoidable. Can you say something similar for the algebraic space?
Oh, that's interesting. I mean, yeah, I don't think it's been looked at, so something else to look at. Yeah.
While MCSP is something that resembles it, but it's not monotone. You said it's not monotone if you increase the circuit complexity. So is there something that is analog to weak MCSP that will be?
Yeah, there is. I mean, so so the question is, so with weak automatability is like monotone, meaning that if like a strong proof system is weak automatable, then a weaker proof system is also weakly automatable. But yeah, like with MCSP, we saw that different circuit classes, say C MCSP, might have completely different complexity to C prime MCSP if C prime is larger than C. It's unclear whether it's harder or easier in general. So I guess Ido is asking about whether there's an analog in the circuit complexity world of like weak automatability, and that analog is improper learning. So if you have like a circuit class and you want to learn circuits from that class, but you allow to learn them by general Boolean circuits rather than just by circuits from that class, that's sort of the analog of weak automatability in the Boolean circuit setting, in the Boolean setting. And indeed, like results for hardness of learning, I mean, hardness of improper learning, all of these results go through crypto assumptions, or assumptions like versions of Feige's hypothesis. And we don't really have like NP-Hardness in that setting. So yeah, so it's kind of like related in a way to the question of whether weak automatability. But for weak automatability, we don't even demand like NP-Hardness, any sort of reasonable hardness assumption that rules out NP-Hardness. That rules out weak automated resolution would be interesting.
Maybe just a comment. It's not a perfect analogy though, because like Boolean circuits can simulate every other circuit model we think of. Well, there is no super proof system driving problem.
Yeah. That's true. Yeah. So like Boolean circuits are universal, but the proof complexity world there's no sort of like. Yeah.
Right, about this public hardness for DNF. You showed in the first slides that there is a new result, but isn't it already known that DNF cannot be popular?
Yeah, so the old result was about packed learning DNS with omega log n terms, and the new result is about packed learning DNS with omega 1 terms. So it's just like a stronger parameter. It's again by Daniel a student here. But they use a different assumption. They use like local PRGs and security of local PRGs for performance here.
So you mentioned this week, automatability question is kind of like open in both directions. Either it can be resolved positively or negatively. Do you have an opinion on this? Or?
I mean, my sort of like default is to assume that things are hard. But I should say that I mean there is something like non-trivial you can do. I think you can kind of like get like a given you can get like 2 to the square root s like time algorithms. So there's like this interesting paper where like the sort of informal connection I was mentioning between learning and automatability is studied in more detail by Tony and others. She's going to mention that in her talk. And so you can use like learning algorithms, like what's known about learning algorithms for DNF. So you know some non-trivial learning algorithms for DNF. You can use those ideas to get weak combinatorial resolution. Or maybe even like strong one.
Let's thank the speaker again, and we'll resume in